In this video, we are going to discuss the first part of Binomial Theorem. We will explore the concept of Binomial Theorem through binomial expansion, in which we will understand the relevance of Pascal's triangle, and we will explore the idea of using the concept of combinations in deciding the coefficients of the terms of binomial expansion. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. Effort has been made to explore the mathematical concepts through the basic ideas in mathematics. First, we will understand what is binomial expansion. In the word binomial, bi means two and nomial means terms. Expression A plus B contains two terms 1 and 2, and if this is not equal to 0, then this is called a binomial expression. For its expansion to happen, we have to give this binomial expression a power. So let us start by power 0. When a plus b is not equal to 0, then a plus b raised to 0 is 1, which is a well-known fact. So its expansion is just 1. Now consider a plus b raised to 1. It will be just a plus b, which we can rewrite as a raised to 1 b raised to 0 plus a raised to 0 b raised to 1. In this expansion, we observe three important things. First is the number of terms in the expansion is one more than the index 1 of the binomial, which is 2. So there are two terms, 1 and 2. Second thing that we observe is that the power of the first term, a, is reducing by 1 in each term. So in the first term, the power is 1. In the second, it has reduced by 1 and becomes 0. On the contrary, power of the second term goes on increasing by 1 in each term. In the first term, the power of p is 0. It has increased by 1 and become 1 in the second term. And the third thing that we observe here is that the sum of indices of the first and the second term in each term is the same. Here 1 plus 0 is 1, 0 plus 1 is 1. Next we consider the binomial a plus b raised to the integral power 2. This is our well-known identity whose expansion is a squared plus 2ab plus b squared. We can rewrite this expansion as a squared b raised to 0 plus 2 a raised to 1 b raised to 1 plus a raised to 0 b square. Here also we observe that the number of terms in the expansion is one more than the index of the binomial, which is 2. The number of terms in the expansion here is 3, 1, 2 and 3. Secondly, we observe that the power of the first term a goes on decreasing by 1 in each term. So in the first term, the power of a is 2. In the second term, it is 1. And in the third term, it is 0. On the contrary, the power of the second term b goes on increasing by 1 in each term. So in the first term, power of b is 0. In the second term, power of b is 1. And in the third term, power of b is 2. And the third observation is the sum of powers of a and b in each term of the expansion is same. Here 2 plus 0 is 2, 1 plus 1 is 2 and 0 plus 2 is 2 again. Next we will consider the binomial a plus b raised to the integral power 3. This is also a well-known identity a plus b cube, which we often write as a cube plus 3a squared b plus 3ab squared plus b cube. We will rewrite this expansion once again. We write it as a cube b raised to 0 plus 3 a squared b raised to 1 plus 3 a raised to 1 b squared plus a raised to 0 b cube. Here also we observe that the number of terms in the expansion is one more than the power of the binomial, which is 3. So the number of terms here is 4. 1, 2, 3 and 4. Our second observation is power of the first term a goes on decreasing by 1 in each term of the expansion. In the first term it is 3, in the second term it is 2, in the third term it is 1, and in the fourth term it is 0. Whereas the power of the second term b goes on increasing by 1 in each term of the expansion. In the first term, power of b is 0, in the second term it is 1, in the third term it is 2, and in the fourth term it is 3. And our third observation is sum of powers of a and b in each term of the expansion is the same. In the first term it is 3, in the second term it is 3, in the third term it is 3, and in the fourth term it is 3 again. You can check these rules to be followed with the binomial a plus b raised to the power 4 to the power 5, so on and so forth. And you will see that all these expansions of these binomials will follow these three rules which we have just verified. You can try it yourself. I think by now we have sufficiently understood how the binomial expansions of integral powers follow three specific rules which we have seen and verified just now. Now we will focus our attention on the numerical coefficients of the terms in the binomial expansion. In the first column, we will write the index which starts from 0, 1, 2, 3, and 4 in this case. So the index here is 0, 1, 2, 3, and 4. And on the right hand side, we will write the coefficients. When the index of the binomial is 0, there will be 0 plus 1, that is one term in the expansion, and its coefficient is 1, which we write next to this 0. When the coefficient of the binomial is 1, there will be 1 plus 1, that is two terms in the expansion, and therefore there will be two coefficients of the term which we write next to this index, and the coefficients will be 1 and 1. When the index of the binomial is 2, there will be 2 plus 1, that is 3 terms in the expansion. So there will be 3 coefficients in the expansion which we write next to these 2. So the coefficients will be 1, 2, and 1 again. When the index of the binomial is 3, there will be 3 plus 1, 4 terms in its expansion when the index is 3. So we will write those coefficients next to this index 3. So the coefficients will be 1, 3, 3, and 1. And when the index of the binomial is 4, there will be 4 plus 1, 5 terms in its expansion. So there will be 5 coefficients in the expansion. Next to this index 4, we write 5 coefficients which will be 1, then 4, then 6, then 4 again, and then 1. So we can go on like that for index 5, 6, 7, so and so forth, and write the corresponding coefficients. There is a specific pattern in the nature of these coefficients. Let us try to investigate this pattern. We observe that when the index is 0, the coefficient is 1. When the index is 1, there will be two coefficients 1 and 1. when the index is 2, the coefficients will be 3, which are 1, 2, and 1. Now here, if we add this 1 and this 1, then we get this 2. When the index of the binomial is 3, the coefficients will be 1, 3, 3, 1, which we can obtain like this. 1 plus 2 gives us this 3, 2 plus 1 gives us this 3, and when the index of the binomial is 4, the coefficients will be 1, 4, 6, 4, and 1, and 1 plus this 3 gives us this 4, then 3 plus 3 gives us this 6, 3 plus 1 gives us this 4. We can perhaps remember this triangle, which incidentally is called as Pascal's triangle after Blaise Pascal, for small integral powers up to say 4 or 5. But what about higher integral powers of binomials? How can we write the coefficients of the terms in the expansion correctly? Is there some means by way of which we can create these coefficients for higher powers of binomial? Let us see. We can create the binomial coefficients in the Pascal's triangle if we have some introductory knowledge of the concept of factorial notation and the concept of combination. N factorial, as it is written and as it is read, is product of n non-negative integers. So therefore 3 factorial means 3 into 2 into 1. 4 factorial means 4 into 3 into 2 into 1. 5 factorial means 5 into 4 into 3 into 2 into 1. So and so forth. We can understand combination in this way. Suppose we have three letters A, B, and C. We denote this number as n equals 3. We have to choose any two letters at a time. We denote this as r equals 2. Then the number of combinations that we can make will be AB, BC, and AC, which are 3 in number. Then how can we calculate these 3? We can calculate these combinations by a combination formula n c r, which is given as n factorial upon n minus r factorial into r factorial. The formula in this case will become 3c2, which will be 3 factorial upon 3 minus 2 factorial into 2 factorial. Now this 3c2 will be 3 into 2 into 1 upon 3 minus 2 is 1 factorial multiplied by this 2 factorial, which will be 2 multiplied by 1. Now this 2 multiplied by 1 cancels with this 2 multiplied by 1, and 1 factorial is 1. So 3c2 will be 3, which is this number of combinations which we have actually found out. Suppose if we have four letters A, B, C, D, so that n becomes 4, we have to select any two letters from them so that r becomes 2. Then we can find the number of combinations as AB, BC, CD, AC, BD, AD, which will be 6 in number. Now we can calculate number of combinations by the combination formula, which will be n c r, which in this case will be 4c2, that will be 4 factorial upon 4 minus 2 factorial into 2 factorial, that will be 4 into 3 into 2 into 1 upon 4 minus 2 will be 2, that is 2 factorial, which will be 2 multiplied by 1. and this 2 factorial, which again will be 2 multiplied by 1. Now this 2 multiplied by 1 cancels with this 2 multiplied by 1, and 2 ones are 2 twos are. So that gives us 4c2 as 3 twos are 6, which is the same number of combinations which we have physically found out. So in this manner we can calculate the combinations of n different objects taken r at a time, given as n c r, which is n factorial upon n minus r factorial into r factorial. Now we will understand how we can make use of the combination formula to calculate the binomial coefficients. We will denote index of the binomial by n and order of the coefficient by r, which may be 1 or 2 or 3 or 4, so on and so forth. We have seen when the index of the binomial is 0, then the single binomial coefficient will be 0c0, which will be by definition 1. Next, when the index n is 1, the first binomial coefficient will be 1c0, which will be equal to 1. The second binomial coefficient will be 1c1, which is equal to 1. When the index n is 2, the first binomial coefficient will be 2c0, which will be equal to 1. The second binomial coefficient will be 2c1, which will be 2. The third binomial coefficient will be 2c2, which will be equal to 1 again. When the index is 3, then the first binomial coefficient is 3c0, which equals 1. The second binomial coefficient will be 3c1, which will be equal to 3. The third binomial coefficient will be 3c2, which will be equal to 3. The fourth binomial coefficient will be 3c3, which will be equal to 1. In this way, you can find yourself the binomial coefficients when the index is 4, 5, 6, etc. by the combination formula which we have used and form the Pascal's triangle. By using combination formula, we can calculate the binomial coefficients directly instead of forming the Pascal's triangle, which will be a bit tedious for higher integral value of the index n. After having understood how to calculate binomial coefficients with the help of combination formula, we are now in position to write binomial coefficients for any integral index. We can write binomial expansion of a plus b square, where n equals 2, as 2c0 a square b raised to 0 plus 2c1 a raised to 1 b raised to 1 plus 2c2 a raised to 0 b square. Here 2c0 will be 2 factorial upon 2 minus 0, that is 2 factorial, into 0 factorial, which by definition is 1. Coefficient 2c1 will be 2 factorial upon 2 minus 1, that is 1 factorial, which again by definition is 1, into 1 factorial, which is also 1. 2c2 will be 2 factorial upon 2 minus 2, which is 0 factorial, which by definition again is 1, and 2 factorial is 2 factorial. So here the binomial expansion will be 2 factorial cancels with this 2 factorial, so it will be 1 into a square b raised to 0 will be 1 plus 2 factorial is 2 multiplied by 1, that will be 2, into a raised to 1 is a, b raised to 1 is b, plus 2 factorial cancels with this 2 factorial, which will be 1 into a raised to 0 is 1 and b square. So finally the binomial expansion of a plus b whole square will be a square plus 2ab plus b square, which is our well-known identity. Binomial expansion of a plus b whole cube, where n equals 3, can be written as 3c0 a cube b raised to 0 plus 3c1 a squared b raised to 1 plus 3c2 a raised to 1 b squared plus 3c3 a raised to 0 b cube. 3c0 will be 3 factorial upon 3 minus 0, that is 3 factorial, into 0 factorial, which is 1 a cube, b raised to 0 will be 1, plus 3c1 will be 3 factorial upon 3 minus 1, that is 2 factorial, into 1 factorial, which is 1 a squared, b raised to 1 is b, plus 3c2 will be 3 factorial into 3 minus 2, that is 1 factorial. 1 factorial is 1 and 2 factorial. A raised to 1 is a b square, plus 3c3 will be 3 factorial upon 3 minus 3, that is 0 factorial, which is 1, and this 3 factorial. A raised to 0 is 1, so it will be b cube. So finally this a plus b cube will be 3 factorial cancels with this 3 factorial, it will be a cube. 3 factorial will be 3 multiplied by 2. 2 factorial will be 2 into a squared b, plus 3 factorial will be 3 multiplied by 2. 2 factorial will be 2 a b squared, plus 3 factorial cancels with this 3 factorial b cube. So finally a plus b whole cube will be a cube, plus this 2 cancels with this 2, 3 a squared b, plus this 2 cancels with this 2, 3 ab squared plus b cube. So this is our well-known identity of a plus b whole cube. Binomial expansion of a plus b raised to 4, where n equals 4, will be 4c0 a raised to 4 b raised to 0 plus 4c1 a cube b raised to 1 plus 4c2 a squared b square plus 4c3 a b cube plus 4c4 a raised to 0 b raised to 4. 4c0 will be 4 factorial upon 4 minus 0, that is 4 factorial into 0 factorial, which is 1 a raised to 4 b raised to 0 is 1, plus 4c1 will be 4 factorial upon 4 minus 1, that is 3 factorial into 1 factorial, which is 1 a cube b, plus 4c2 will be 4 factorial upon 4 minus 2, that is 2 factorial into 2 factorial a squared b squared, plus 4c3 will be 4 factorial upon 4 minus 3 factorial, which is 1 factorial, which is 1 multiplied by 3 factorial a b cube, plus 4c4 will be 4 factorial upon 4 minus 4, that is 0 factorial, which is 1 upon 4 factorial. A raised to 0 will be 1 and b raised to 4. 4 factorial upon 4 factorial is 1. So a raised to 4 plus 4 factorial is 4 into 3 into 2. 3 factorial is 3 into 2 a cube b, plus 4 factorial will be 4 into 3 into 2 upon 2 factorial is 2. Again 2 factorial is 2 a squared b squared, plus 4 factorial is 4 into 3 into 2 upon 3 factorial is 3 into 2 a b cube. 4 factorial cancels with this 4 factorial and it will be b raised to 4. So finally we get a plus b whole raised to 4 equals a raised to 4 plus 3 into 2 cancels with this 3 into 2 and it will be 4 a cube b plus this 2 cancels with this 2, 2 ones are 2 twos are, so it will be 3 twos are 6 a squared b squared plus 3 multiplied by 2 cancels with this 3 multiplied by 2 plus 4 a b cube b raised to 4. So this will be the expansion of a plus b whole raised to 4. Before we start solving problems, let us get acquainted some shortcuts in the calculation of combinations. For example, 5c0 will be 5 factorial upon 5 minus 0, that is 5 factorial, multiplied by 0 factorial. So since this 5 factorial cancels with this 5 factorial and 0 factorial being 1, 5c0 works out to be 1. Therefore, in general, any combination nc0 is always 1. The combination 5c1 will be 5 factorial upon 5 minus 1, that is 4 factorial, into this 1 factorial, which is 1. So therefore this will be 5 multiplied by 4 factorial upon this 4 factorial cancels with this 4 factorial, giving us 5. So therefore in general we can say that nc1 is always equal to n. 5c2 will be 5 factorial upon 5 minus 2, that is 3 factorial, multiplied by this 2 factorial, which will be 5 into 4 into 3 factorial upon 3 factorial into 2 factorial. So 3 factorial cancels with this 3 factorial and 2 factorial is 2. So it will be 2 ones are and 2 twos are. So that gives us 5 twos are 10. In case of 5c3, it will be 5 factorial upon 5 minus 3, which is 2 factorial, multiplied by 3 factorial. Now this is same as this. So therefore its value will also be 10. So we conclude that 5c2 is same as 5c3, or in short we can say that NCR is same as NC R minus 1. Here if R is this 3, then R minus 1 will be this 2. So you can remember this formula so as to avoid repeated calculations. Next we will see how to calculate 5C5. It will be 5 factorial upon 5 minus 5, that is 0 factorial, which is 1, multiplied by this 5 factorial. So the same terms are coming in the numerator and denominator, which get cancelled and it gives us 1. So therefore in general we can say that n c n equals 1. So this is another shortcut that we found. So these four shortcuts so that we can calculate the coefficients of the expansion quickly. nc0 is 1, nc1 is n, then ncn is 1, and ncr is same as ncr minus 1. Binomial expansion can also be used to find the values of higher powers of large numbers. For example, we will find 96 cube. Here we will express this 96 as a sum or difference of a binomial of two suitable numbers, such as 100 minus 4, and write 96 cube as 100 minus 4 whole cube. Now we can find its binomial expansion by treating 100 as a and minus 4 as B and 3 as N. So this binomial expansion will be 3C 0 100 cube into minus 4 raised to 0 plus 3C 100 square into minus 4 raised to 1 plus 3C 200 raised to 1 into minus 4 square plus 3C 300 raised to 0 into minus 4 cube. We know 3C0 is similar to NC0, which we know is 1. So this will be 1 into 100 cube. That will be 0, 0, 0, 0, 0, 0. Minus 4 raised to 0 will be 1 plus 3C1 is similar to NC1, which we know is N. So this will be 3 into 100 square will be 0, 0, 0, 0 multiplied by minus 4 raised to 1. So that will be minus 4 plus 3C2 is 3 multiplied by 2 upon 2 factorial is 2 multiplied by 100 multiplied by minus 4 square will be 16 plus 3C3 is similar to NCN, which we know is 1. So this will be 1 multiplied by 100 raised to 0 will be 1 again multiplied by minus 4 cube will be minus 64. Next it will be 1 0 0 0 0 0 0. This will be 4 threes are 12 minus 12 1 2 3 4. This 2 cancels with this 2. 16 threes are is 48. So that will be plus 4800 minus this 64. First we will add this 1 million with this 4800. So that will be 1004800. Then we add this 1,20,000 with this 64. Subtract it from here. So that will be minus 1 2 0 0 64. 10 minus 4 is 6, 1 carry. 10 minus 7 is 3, 1 carry. 8 minus 1 is 7, 4. 10 minus 2 is 8, 1 carry. 10 minus 2 is 8, 1 carry. 1 minus 1 is 0. So therefore 96 cube is this 884736. So this is how we can find 96 cube by using binomial expansion. In the next problem, we have to find which is the larger number, 1.01 raised to 1 million or 10,000. To find this out, we will write this 1 plus 01 raised to 1 million as 1 plus 0.01 raised to 1 million, where this 1 is A, this 0.01 as B, and this 1 million is N. So, binomial expansion of 1.01 raised to 1 million will be 1 million C 0 into 1 raised to 1 million, which will be 1 only, into 0.01 raised to 0 plus 1 million C 1 1 raised to 1 million minus 1, which will be 1, and 0.01 raised to 1 plus the remaining positive terms, which need not be calculated. This is similar to NC0, which we know is 1. So this will be 1 into 1. This 0.01 raised to 0 will be 1. So this will be 1 into 1 into 1, that is 1, plus 1 million C1 is similar to n C1, which we know is n. So this will be 1 million multiplied by this 0.01 plus the remaining positive terms. This will be 1 plus 1 million multiplied by 0.01 will be 10,000 plus the remaining positive terms. Summation of all these things is definitely going to be greater than this 10,000. because here 10,000 plus 1 plus positive terms is here. So therefore, obviously 1.01 raised to 1 million is greater than 10,000. We have to find a plus b raised to 4 minus a minus b raised to 4, and hence we have to evaluate root 3 plus root 2 raised to 4 minus 3 minus root 2 raised to 4. Let us first calculate a plus b raised to 4. So according to binomial expansion, we have a plus b raised to 4 will be 4 c0 a raised to 4 b raised to 0 plus 4c1 a cube b raised to 1 plus 4c2 a squared b squared plus 4c3 a raised to 1 b cube plus 4c4 a raised to 0 b raised to 4, and a minus b raised to 4 will be 4c0 a raised to 4 b raised to 0 minus 4c1 a cube b raised to 1 plus 4c2 a squared b squared minus 4c3 a raised to 1 b cube 4c4 a raised to 0 b raised to 4. Now we have to subtract a minus b raised to 4, which is this, from a plus b raised to 4, which is this. Therefore, we have to change the signs of the expansion of a minus b raised to 4. So this first term, which is plus, will become minus. The second term, which is minus, will become plus. The third term, which is plus, will become minus. The fourth term, which is minus, will become plus, and the fifth term, which is plus, will become minus. So therefore, a plus b raised to 4 minus a minus b raised to 4 will become, now here 4c0 a raised to 4 b raised to 0 cancels with this one, then 4c2 a square b square cancels with this, and 4c4 a raised to 0 b raised to 4 cancels with this. So what we are left with is 2 times this term, which is 4c1 a cube b raised to 1, and plus 2 times this term, which is 4c3 a raised to 1 b cube, which will be 2 times. Now this 4c1 is similar to n C1, which we know is n. So 4c1 will be 4 a cube b, plus, now we know that this 4c3 is same as 4c 4 minus 3, that will be 4c1, which is similar to n c1, which we know is n. So therefore this 4c3 will be 4 itself a b cube. We will write this 2. We will take this 4 common and ab common from these two terms into a square plus b square, which will be 8ab a squared plus b squared. Now we have to evaluate this. So what we do, we put this root 3 in place of this a, root 2 in place of this b, root 3 in place of a, root 2 in place of b. So therefore, root 3 plus root 2 raised to 4 minus root 3 minus root 2 raised to 4 will be 8 times. We have a equals root 3, b equals root 2, then a square, that is root 3 square, will be 3, and b is root 2, and root 2 square is 2. So that gives us 3 plus 2, 5, 5 8s are 40, and root 3 multiplied by root 3 is root 6. In the next problem, using binomial theorem, we have to prove that 6 raised to n minus 5n always leaves a remainder 1 when divided by 25. Here, this 6 raised to n minus 5n is the dividend, 1 is the remainder, and 25 is the divisor. Now, according to division algorithm, we know that dividend, which is 6 raised to n minus 5n, equals the quotient, say k multiplied by the divisor, which is 25, plus the remainder, which is 1, which we will write 25k plus 1. We have to prove 6 raised to n minus 5n equal to 25k plus 1. Now we will split this 6 in the binomial as 1 plus 5 raised to n, whose binomial expansion will be n c0 1 raised to n 5 raised to 0 plus nc1 1 raised to n minus 1 5 raised to 1 plus nc2 1 raised to n minus 2 5 squared plus nc3 1 raised to n minus 3 into 5 cube plus so and so forth plus ncn 1 raised to n minus n, which will be 0 into 5 raised to n. This will be equal to nc0 is 1, 1 raised to n is 1, 5 raised to 0 is 1. So the first term will be 1 plus nc1 is n raised to n minus 1 is 1, 5 raised to 1 is 5, plus in the successive terms we can take this 5 square as a common term. So this will be 5 square into bracket, it will be nc2, which is this, then this will be 1 plus this nc3, this will be 1, 5 cube divided by 5 square will be 5 plus so and so forth plus ncn will be 1, 1 raised to 0 will be 1, and this 5 raised to n will be 5 raised to n minus 2, because we have taken 5 square common from it. Now here, for any non-negative integer n, this whole bracket will be a constant k, and this 5 square is 25. So we get 1 plus 5 raised to n, that is 6 raised to n, equals 1 plus this 5n plus this 25k, which we can rewrite as 6 raised to n minus this 5n equals 25k plus 1, which is exactly what we have to prove. So hence the statement is proved. In the next problem, we have to show that 9 raised to n plus 1 minus 8n minus 9 is divisible by 64, where n is a positive integer. Now 9 raised to n plus 1 minus 8n minus 9, which is a dividend, is divisible by 64, which is a divisor. Then according to division algorithm, we can write that the dividend 9 raised to n plus 1 minus 8n minus 9 divided by 64 is a positive integer, say k. So therefore we have to prove that 9 raised to n plus 1 minus 8n minus 9 divided by 64 is k. Now we will split this 9 in a binomial 1 plus 8, and we will raise it to the power n plus 1, whose binomial expansion will be n plus 1 1 raised to n plus 1 into 8 raised to 0 plus n plus 1 c1 into 1 raised to n into 8 raised to 1 plus n plus 1 c2 1 raised to n minus 1 8 squared plus n plus 1 c3 1 raised to n minus 2 into 8 cube plus so and so forth plus n plus 1 c n plus 1 1 raised to n minus n, which will be 0, and 8 raised to n plus 1. N plus 1 c0 will be 1, this will be 1, and this will also be 1. So the first term will be 1. In the second term, n plus 1 c1 will be n plus 1. 1 raised to n will be 1, 8 raised to 1 will be 8. In the next term onwards, there are integral powers of 8, 8 square, 8 cube, 8 raised to 4, so and so forth, and finally 8 raised to n plus 1. So we will take 8 square common from all these terms and write 8 square into bracket this n plus 1 c2, 1 raised to n minus 1 will be 1, plus this n plus 1 c3, 1 raised to n minus 2 will be 1 again, and 8 cube divided by this 8 square will give us 8 plus so on and so forth plus n plus 1 c n plus 1 will be 1, 1 raised to 0 will also be 1, and this 8 raised to n plus 1 divided by 8 square will give us 8 raised to n plus 1 minus 2. So that will be n minus 1. Now for any positive integer n here, this whole bracket will be a positive integer k. So this will be 1 plus 8, which is 9 raised to n plus 1, equals this one plus, opening this bracket with this 8, it will be 8n plus this 8 plus this 8 square, which is 64, multiplied by this k, which will be 8n plus 8 plus 1 9 plus 64k. We will move this 8n plus 9 to the left hand side and write 9 raised to n plus 1, which is this, minus 8n minus 9, which is this, divided by this 64 will give us this k. So this is nothing but exactly what we have to prove over here. So hence we have shown that 9 raised to n plus 1 minus 8n minus 9 is divisible by 64 for any positive integer n. Friends, if you like this video, please click the like button, share this video with your classmates. Don't forget to subscribe this channel to get more videos of this type. Give your comments to make these videos better. You can suggest topics on which you want me to make videos. See you in the next video. Until then, keep watching Number Collage. Thank you.